Physical Science, this is Mr. B, and today with this video we are starting Chapter 5, and the title of that chapter is The Periodic Table. And most of you, well, if you pay attention, you see this every single day when you walk into my room. It's hanging up in the back really big. It's been in every single one of your science books, probably for multiple years now. And in this chapter, and another Mrs. B-ism is that you may see it periodically, which you're going to kind of have to realize that that's going to kind of help us understand the meaning of what the periodic table actually shows. So in this chapter, we're diving more in depth with what the periodic table actually is, how it was set up, how it is organized, the different groups, and all the things like that. So there's going to be a lot that goes into that periodic table. Again, it just looks like a big complicated chart, but there is a very specific reason why it's organized the way it is. And to start, our first section is titled Organizing the Elements. And of course, we always start with our little comparison here. It says, in a video store, movies are in categories such as action or comedy. When scientists organized the elements, they had to decide what categories to use and where to place each element. An organized table of the elements is one of the most useful tools in chemistry. So just like we arrange movies in a video store, again, it'd be pretty hard if we were looking for a comedy and they just had movies smattered all over the place and no rhyme or reason, no actual place. Again, when we put things in order, it really helps us out. And that's not just for the elements and for chemistry, it's for real life in general. So this is no different. So how the search kind of began, kind of really started taking our, in the 1750s is when it really, someone first started taking a look at it. Because at this point, scientists had identified only 17 elements, which were mainly in metals, one example being copper and another one being iron, and as the number of elements grew, so did the need to organize them into groups based on their properties. So around this time, there was only 17 elements, and even at that, people were like, man, we really need to start figuring out a way to organize this. So in 1789, I would definitely write this guy's name down. Antoine Lavoisier, so he's French, that's how you pronounce his name, Lavoisier, grouped the known elements into categories that he called metals, non-metals, gases, and earths. And for the next 80 years, scientists looked for different ways to classify the elements, but no system worked for all the known elements. So he kind of gave it the best shot. People kind of accepted his ideas, but they knew that there was a better way to do it, but they really just couldn't figure it out at the time. So for 80 years, scientists were looking for ways to kind of improve upon, again, what Lavoisier tried to do. And so a guy by the name of Mendeleev came around, and he's going to be the one to pretty much solve our problem of how to organize the elements for us. So Mendeleev is his name, and I would make sure we wrote his name down. And how he did it, so we'll talk about exactly how he did it, but a big kind of overriding statement of what he actually accomplished is what he arranged the elements into rows in order of increasing mass so that the elements with similar properties were in the same column. So knowing the difference between a row and a column is going to be big when we talk about this chapter. So he arranged the elements into rows in order of increasing mass so the elements with similar properties were in the same column. And how did he do this? So it's actually kind of a really interesting story about how he did this. So in the 1860s, Dmitri was his first name, that's how you pronounce it. Dmitri Mendeleev developed an approach for organizing the elements while playing the card game Solitaire. Now I can tell you just because of how interesting that is, that's definitely going to be a question on your quiz tomorrow. So I definitely make sure I wrote down that he invented the way of organizing elements while playing the card game Solitaire, and in this game the player sorts a deck of cards by suit and value. So over here on the right, so hopefully you guys have all played Solitaire, probably done it on your computer before. Again, you have to start with the aces, then with the ace of diamonds you put the two of diamonds, and then so on until you organize all of the cards just like that. So he was playing that game, and that kind of gave him an idea of how he could organize the elements. So what he did is he made a deck of cards, in quotes there, of the elements. So on each card he listed the element's name, he listed its mass, and he listed properties. And when he lined the cards up in order of increasing mass, a pattern emerged, and the key was to break the elements into rows. So he organized, if we look here, he organized the elements in rows, going from, again, a row is from left to right, a column is up and down. So he went from left to right in order of increasing mass. So the smallest one, hydrogen equals 1, started over here on the left. We have lithium 7. I believe that's going to be beryllium 9.4, boron 11, carbon 12, nitrogen 14, oxygen 16, fluorine 19, and then you can see the numbers just keep getting bigger as we go across the rows. So that is how he organized his elements. He organized them based off of mass, and he organized them into rows, and he started to notice different patterns emerging. And his final arrangement was similar to a winning arrangement in solitaire, except the columns were organized by properties instead of suits. And within a column, the masses increase from top to bottom. So not only did the masses increase going from right to left, they increased from going top to bottom as well. So he was noticing definite patterns emerging when he organized it in this manner. And Mendelev's chart was a periodic table, and a periodic table, so I definitely write this down, is an arrangement of elements in columns based on a set of properties that repeat from row to row. So that is kind of confusing, but basically what it's saying is that there are going to be patterns developing when we go from row to row as well from the column. So up and down we're going to have patterns, and from right to left we're going to have patterns, which is really pretty unique and pretty cool way to organize things when you think about how long ago he did this, and the fact that when he did this, a lot of the elements were unknown, and he was still able to correctly predict how these things would lie. And we're going to see actually here in a second of what happens about he was actually able to predict what new elements might look like as well. And that's kind of what this next one's going to be saying here. So at the time when he made his table, many elements had not yet been discovered, and when he placed the elements with where their properties fit, there were several gaps in the table. So when he noticed that there was an element that did not meet the set pattern that he's seen follow, so he just left a gap there. He didn't try to squeeze and say, okay, well maybe it's this known element that we already have. He said, you know what? There's no element that we know right now that describes that would fit this pattern, that would have these properties, so I'm just going to leave it blank for now. And so, however, he left it blank, but he was still able to offer the best explanation for how the properties of an element were related to its location in the table. So he was saying that, again, even though there's blank spots, I still think, for the most part, everywhere I have everything that's known, I think it's going to work out pretty well. So I may not have all the answers right now, but what I have is correct, and it's going to actually give us the tools to make future predictions and to place things in when we make more discoveries. And again, he was confident in the gaps in his table would be filled by new elements, and he used the properties of elements located near the blank spaces in his table to predict the properties for undiscovered elements. And however, some scientists did not think that that was going to be correct. They said, you know what, I don't think your predictions are going to be correct, but on the flip side, others used the predictions to help in their search for undiscovered elements. So in the blank spots, it wasn't like people just gave up. That was almost kind of like something that everyone really wanted to fight for, wanted to maybe be able to discover, well, let's see if he's right. Let's see if I can find an element that fits where this blank spot should be. And so we are going to keep going about what evidence helped verify the usefulness, and that's going to be probably the fact that people started discovering some elements. And the close match between Mendelev's predictions and the actual properties of new elements showed how useful his periodic table could be. So we're going to see a couple real-life examples of elements that were discovered that fit perfectly into blank spots that he made. So Mendeleev named missing elements after elements in the same group. So for example, he gave the name EKA aluminum to the missing element one space below aluminum. And so he predicted that this EKA aluminum would be a soft metal, would have a low melting point, and would have a density of around 5.9 grams per centimeters cubed. So that was his prediction. He thought, you know what? I don't know what this element is, so I'm just going to call it EKA aluminum, and this is what I think it's going to look like. And so in 1875, there was a French chemist who discovered a new element, and he named the element gallium in honor of France. The Latin name for France is Gallia, and gallium turned out to be a soft metal, has a melting point of 29.7 degrees Celsius, which is fairly low, and it has a density of 5.91 grams per centimeters cube. And when we look at the slide before, that's almost exactly what Mendeleev predicted. So this is a lot of strong evidence that the way Mendeleev had his table arranged was the correct way. And just kind of some real-life uses for gallium is it's used in some traffic signals that emit that are tiny light-emitting diodes, or LED lights, and they contain a compound of gallium. So gallium is actually used quite a lot in a lot of our LED lights. And scientists use a periodic table to explain the chemical behavior of different groups of elements. So the properties of gallium were remarkably similar to the predicted properties of EKA aluminum. Scientists then were able to conclude that gallium and EKA aluminum are in fact the same element, so he did in fact predict the properties of the undiscovered element. And the discovery of scandium in 1879 and the discovery of germanium in 1886 provided more evidence to support that Mendeleev had it correct. So that's it for our first video for Chapter 5. Let me know if you have any questions.